one of this topic, we are going to talk about synaptic circuit. Anybody has any idea about the first word? Circuit, we all know. What is?
Synaptic means the connection with the neuron.
Yes. So then the next question is, do you know what is synapse?
The connection between the forgot. It's the end of the neuron cell and the beginning of the neural cell. There is a connection. It's called synapse.
Yes, exactly. You're 100% accurate. Very good. So these synapses are the connections between human brain cells, the neurons, through which all the communication signals and everything, pulses that travels from one neuron to another neuron. So one of the biggest dream for the scientific community is to create an artificial human brain. And the ability to create an artificial human brain depends on ability to mimic the behavior of human synapse. And people have tried to come up with many different ways and means to mimic the behavior of human synapse. And one of the easiest way to come up with an electrical circuit that can behave like a synaptic node. So if you can add millions and billions of those circuit nodes and create a gigantic system, they think that it can mimic the behavior of human brain. So IBM, that Deep Blue project, it has been there for more than 50, 60 years. IBM was, right from the beginning of computing era, IBM was trying to come up with something, some gigantic system to mimic the human brain behavior. So in this lecture, in this part, we are going to talk about some of the attempts in this research area where scientists tried to mimic the behavior of human synapse by developing some synaptic circuit. So, cerebral cortex, we all know this is the frontal part of our human brain. This superficial layer, that's where our memory, our attention, our perception, our awareness, our language skill, our consciousness, our thought process, everything is controlled from this cerebral cortex area, right? So what is cerebral cortex is made of? Cerebral cortex is made of about 100 billion neurons, right? And each neuron has an average of 10,000 to 100,000 distinct synapses. So neurons are made of many synaptic nodes, synapses. So that means we are talking about if we want to mimic the behavior of cerebral cortex, we are talking about 100 billion times 100,000 synapses we have to basically mimic. So we are talking about, this is 100 billion means it's 10 to the power 11. So that is 1, 2, 3, 4, 5. So we're talking about 10 to the power 16. That number of synapses we have to mimic if we want to be just mimic the behavior of cerebral cortex. So what is synapse? As you mentioned, biological synapse is a junction through neuron signals to each other. So some graphical representation of synapse. This is how a synapse looks like, a synaptic joint, joint between two neurons. So now, through this joint, not only electrical pulse, there are many other electrochemical communication that will take place through these joints that will give rise to all of the actions, our memory, our attention, perceptions, awareness, thought, language, and consciousness, all of the actions and reactions, our emotions, everything will be reflected determined based on the electrical, electrochemical, and mechanical signals that flows through these synaptic joints, biological synapse. So it's a very complex, not only electrical, it's electrochemical, electromechanical, so as well as electrical and electromagnetic signals that will go through these joints. So one thing is that in regular physical system, like in computer or any other electronic device, we determine the parameters, physical, electrical, material parameters on both sides of the junction, those remain constant. But here in synaptic joint, before and after, in time as well as in space, these synapses, they can change their properties, they change their activities. So it is much more complex than regular physical system. So biological synapse, what they do, they pass information from presynaptic cell to postsynaptic cell by neurotransmitter. So synapse is made of many different components, and one of the critical component is the neurotransmitter, which is like equivalent to the transmission line for an electrical system. The interconnect line, it is transferring signal from one transistor or one computer core to another core. It's like signal bus. So the neurotransmitter in the synapse is like the signal bus in our modern day computer, right? So within presynaptic nerve cell, vesicles containing neurotransmitters sit at the synaptic membrane. So, and then arrival of any action or reaction produces some voltage potential, some changes in charge, which will be reflected through the changes in the concentration of some ions. And the concentration of these ions will vary depending on the voltage or the potential that is applied or generated. It is coming from different parts of the body. So even like you see that I suffered with this vertigo once or twice. What is vertigo? There is some calcite, some particle inside your cochlear canal, the ear canal, eardrum. If somehow it is stuck into inside, or it creates an imbalance, right? So my doctor first time told me that your natural GPS system somehow got disoriented. So that's why I was not able to stand still. So I had to call 911 because I thought I was having a stroke or something. So it's that kind of experience. So it's simple, some calcite, calcium ion keeps the balance of physical balance, because if you move this, it will automatically like this. So it will always keep its balance horizontally, so that at any physical position you can actually maintain your stability.
Like gyroscope.
Yeah. So it is, and same thing here in human brain. We are basically experiencing the changes in some ion concentration due to the changes in electrical potential. And these chemical ions, they trigger biomedical reactions that results in some sort of signal to be traveled or released by the presynaptic side, and it will be basically traveling through the transmitter and synaptic cleft. What is synaptic cleft? This is basically the synaptic cleft. This kind of gap area between the two sides of the synaptic joint. The signal will basically travel, must penetrate through this cleft. It's like the insulator layer inside your transistor. So what we're trying to understand, trying to relate how the synaptic behavior can be related to an electrical circuit behavior. In electrical circuit, what we are doing, due to the application of potential or any signal, there is an electron balance or charge carrier balance or imbalance created that will force electron to flow in this direction and this direction, and we are interpreting that as a positive signal or negative signal, high signal or low signal, binary 1 or binary 0, right? That's how it's same thing with the application of certain potential. There are some electrochemical, electromechanical processes going on which result in the change in ion concentration, and then change in ion concentration will be felt or will be traveled through those clefts through the neurotransmitter, and that will be registered as our action or reaction of human brain. So, some of the challenges scientists faced is to characterize the correct behavior of synapse. So it is a complex physiology because the signals that they are going to handle, the synapse, this is not purely electrical, this is not, sometimes it is chemical, sometimes it is mechanical, sometimes it is electrochemical, sometimes it is electromechanical signal. And so that's why it is very, very difficult to characterize it using one set of variables or one set of mathematical equations. And also further complicating the situation, the transmitter's behaviors, like our regular bus, we know exactly this is 256-bit bus. It is made of copper wire, and we can expand certain type of resistance, capacitance, inductance, some parasitics from this wire, and how it will vary with temperature. But here, these transmitters actually, their behavior does not remain constant. So it will vary depending on the situation. Like for example, if you think about, if you are afraid of something, we are 7 persons in this room. 7 of each of us will react to a threat differently. Some of us are more brave than some of us are less. Like, for example, particularly if I ask you to walk through a deep dark forest in the middle of the night, some of us will be brave enough to try it, some of us will be really, really afraid, right? So it's that the fear factor or the factors that will affect our brain, that part, the fear part of our brain, will be very depending on person to person, right? So if deep down, that means all the synapses, they're adjusting their physical and other properties accordingly, right? So now the question is, and there has to be a way to measure how this transmitter will react to certain excitation or certain potential. And one of the measuring unit is called postsynaptic potential, PSP. So the concentration of transmitter release can affect the height and the duration of this PSP. This potential, you can basically consider it as an electrical pulse, as a voltage pulse. It will have a duration, it will have a magnitude. So, as I said, the degree of fearfulness among 7 of us will vary for the same fear factor. That means deep inside our transmitter, the width and the magnitude of the PSP will be different for different person for the same set of factors, right? So that is one measure of, because deep down, what we are trying to do, we are trying to come up with something to mimic the behavior of biological synapse using an electrical circuit which can produce that electrical behavior, mimic that electrical behavior, and that electrical circuit must have some IV characteristics. A second area of complexity in understanding biological synapse is the ion channel. It is a molecular structure that blocks or that permits flow of ion through the cell membrane. So, it is like the interconnect channel. It will have its property, resistance, capacitance, inductance, and all conductance, all of those that will kind of interconnect parameters permits free flow of electrons. Similarly, these ion channels that will carry those calcium or whatever ion concentration, their molecular structures and their conductivity and other properties will affect the behavior or the functioning of biological synapse. So, if we want to summarize the 5 critical attributes or properties or characteristics of biological synapse, these will be: when synapse is not learning, the memory is non-volatile. What does it mean? So that means synapse will remember the experience, the information about prior experience, because we human or any living being, we act on our prior experience, right? The information that is set in our, like if you have a small baby, if that baby touches a light, is hot, after 1 or 2nd or 3rd times, he or she will not touch that light, because that memory will react that, well, if you touch that light, hand will burn. So when the synapses is not learning new thing, it is acting like a non-volatile memory. That means it is, it can preserve the information as it is. And when it is learning, the updates in the memory are bidirectional. That means it can basically, based on the prior information, your current action will be determined, and based on your current action, your memory will be updated. So it's a bidirectional connection. So the second criteria is the synapse output is the product of the input signal and the stored memory value. That means as you are experiencing something currently, based on that new input signal and the previously whatever I have stored in my memory, prior experience, together the outcome will be determined. What action I will take. Should I cross that path or not? Based on my prior experience as well as current situation. Together, so it's like a sequential circuit. If you remember, introduction to sequential circuit, the output based on the current combination of input and signals taken out of from the memory based on the previous input. So it's like a sequential circuit. So we find some similarity. Memory reading and writing can occur simultaneously. That means as we are experiencing a new thing, we are not only doing it, we are not only taking in new information, simultaneously we are also updating what we have stored in our memory from previous actions. That means memory reading, retrieving information from previous experience and updating it. This can happen simultaneously. Memory updates vary with both input signal and stored memory. So they, again, based on the current situation and previous experience, memory will be updated. Synapse can be considered as compact, first, very low energy consuming biological device that has the ability to process the signal as well as store information. So in conventional von Neumann computing model, you have a memory unit, you have a signal processing unit, you have an input unit, you have an output unit, right? And control unit. But in here, our synapse, not only it stores information, it also processes information, takes actions and reactions. So, looking at these 5 attributes of synapses, what we are basically can summarize if we want to build a system to mimic biological synapse. We need bidirectional memory capacity. We need a memory unit that can read, write simultaneously, and it can update its information while it is performing a task. And the memory needs to be non-volatile. At the same time, this biological unit it is not only a information or signal storage unit, it is also a signal processing unit, because it will determine the action or reaction to certain factors or experience, right? So that means it is a merger of conventional ALU unit and the memory unit together. That is, we call it in-memory signal processing, in-memory arithmetic signal processing, right? So now, based on these understandings and findings, what we have just summarized, its similarity with modern day computing system, similarity and contrast, people have tried to come up with synthetic cortex, cerebral cortex, for last few decades. It has been there for more than 50, 60 years. Still, it has been a very, very challenging task. So one of the earlier project was to develop a silicon-based cortex. So it's basically what they're trying to do. As the information processing capability of silicon devices like transistor continuously increase, they try to utilize that increasing signal processing capability of silicon device to mimic the or emulate the behavior of the human cortex. But the problem is that they needed like billions and billions, trillions of silicon devices. The overall noise, power consumption, thermal stress, and other complexity actually went beyond what they could control. So complete implementation of a whole cerebral cortex was never possible because of many practical limitations, but they tried to develop bits and pieces. Another basically effort was biomimetic circuit. So biomimetic circuit, these are a specialized electrical circuit that can emulate the behavior of individual neurons. While implementing a complete silicon cortex is challenging, is very difficult. So how about we come up with some circuit that can mimic the behavior of individual neurons? That is actually another separate branch of biomedical research called biomimetic circuits. The circuits that can mimic the behavior of individual human neurons. Some of the earlier original research done by some of the legendary biomedical circuits and system researchers in this area on artificial. One of them is artificial retina by Mead. This gentleman is one of the pioneer in analog and neural circuit. So he has this book or big publication where he elaborated the circuits he proposed for an artificial retina design. And Chris Durio, single transistor synapse, it was a very revolutionary proposal. He tried to mimic the behavior of a synapse with one single transistor, part of it, and it published in 1996 in Electron Device Journal. And Ellis Parker carbon nanotube-based synaptic circuit, he tried to do it in 2007. These are some of the important work. It was never fully successful, but it was groundbreaking at that time because they tried to completely change their way we think and come up with some revolutionary idea. So now, if you really want to implement a synaptic circuit using silicon device, so what are the expectations? If you want to take this as a research challenge, your synaptic circuit must be capable to emulate the complex behavior observed in biological synapse. It's not like a binary signal. It's much more complex than that. So it has to be a very super efficient analog circuit, analog mixed signal circuit. It is not going to be a simple digital circuit, right? To emulate every detail of biological synapse behavior is impractical. It is impossible because we cannot take care of so many different factors and variables just by using one analog mixed signal circuit. So what they try to do, they try to identify one or two or a small subset of dominant factor or behavioral aspect of synapse and emulate that only using this behavior. So that's why we cannot emulate all the detailed biological and physiological behavior of biological synapse. We have to select a small subset of this complex system, a small subset of factors of this complex system, and we can do emulate. So they are based on the, like any living system, based on the research, they concluded that there are some aspect of synapses behavior that will be very critical and important. Those factors will determine the functioning of synapse more than any other factor. So they try to concentrate on their effort to mimic those dominating factor in the circuit they try to design. So if you want to develop a synaptic circuit using any nanoscale circuits and devices, what are the main considerations if you want to develop a model? Come up with a non-volatile, very efficient non-volatile memory storage that can store the synaptic information and that is comparable to the synaptic strength. Estimate and emulate biomimetic response of synaptic cells. So these are, this is another group. They tried to, in early 2000, they tried to come up with some efficient FPGA based. I'm just giving you for your reference if you want to basically do further study in that area. So this is another group. They actually worked on FPGA based synaptic circuit. Hugo Garis. They presented their concept in Artificial Intelligence Conference in 2008. This is also an important work. In 1996, we already mentioned this Chris Doriu's work and Mead's work. What are the main aspects of this work? In their proposed work, they used a hot electron injection based or tunneling mechanism based devices to mimic the bidirectional memory behavior. And if those who have taken VLSI course, particularly in memory lecture, you have learned about floating gate device. A floating gate device is the fundamental building block of all the flash memories, your SIM card, your pen drive, all the flash memories. The fundamental building blocks of all the flash memories are floating gate device. Floating gate device works on electron tunneling from channel to a floating gate. So they also tried to use the same mechanism, the non-volatile transistor for non-volatile memory, flash memory, which is dependent on electron injection to basically implement the bidirectional memory function requirement for synaptic circuit. But the problem is a single transistor can hardly emulate the temporal continuous response of a very, very small amount, but when you have a large array of synaptic circuit, or even in same synaptic node you have like many neurotransmitter, then you cannot emulate all the behavior. So the other problem is a single transistor. If you look at the IV characteristics of a single transistor, IV characteristic is continuous characteristics in time. You apply voltage. What is IV characteristic? Is the relation between voltage and the current across any electrical device. And it's a single continuous line in time domain. However, in actual synaptic circuit, it will not follow a continuous line. Sometimes it will be abrupt up and down. So it will not be a continuous temporal response. So that is another problem. So Alice Parker designed this carbon nanotube based synapse. So because he tried to develop it using nanometer scale carbon nanotube, it consumed very small area and it provided very similar response to biological synapse. But the problem is, but basically implementation, design and implementation of carbon nanotube in desired factors, forms and properties still very challenging, but this was mostly a theoretical work. So as a whole, the biomimetic circuit or synaptic circuit, that area still is kind of under development. 3 decades ago, it got tremendous amount of interest, but there was no significant breakthrough, but still it's a research area, ongoing research area. So this is basically a cross-sectional diagram of the single transistor synaptic circuit implemented by Chris Duriu and Mead's project, and they used an N-type MOSFET transistor to implement their single transistor synapse. But they tried to very small subset or 1 or 2 characteristics of synaptic behavior. So this single transistor learning device or synaptic device, they integrated it on a non-volatile analog memory storage with bidirectional memory capability. And as I said, the single transistor synapse was implemented using an N-type MOSFET. So, if you basically, as I mentioned, if you remember the introduction to VLSI class, whenever you need memory function, particularly non-volatile memory, you need a floating gate transistor. You have a regular gate, you have a floating gate, and the transistor channel inner gate. So in this single transistor synaptic circuit, they used a floating gate with a polycrystalline layer 1, a control gate with outside layer, and moderately doped channel and lightly doped drain. So this is basically a floating gate transistor they used. And as I mentioned, the functionality of floating gate transistor depends on a tunneling mechanism, tunneling of hot electron from channel to the floating gate. And that tunneling mechanism is called Fowler-Nottingham tunneling. So the operating principle, the working principle of the single transistor synapse is exactly like the floating gate transistor you have seen in introduction to VLSI design. So those who have not taken VLSI class, just take any basic VLSI book and you will see actually how all the detail, because I don't want to go that route because that will take 1/2 lecture to explain how floating gate transistor is designed and works. I have to bring that VLSI lecture again. But the operating principle, the working of the single transistor synapse is exactly like a floating gate transistor. So what are the limitations of these projects? One of the limitations is the single transistor silicon synapse can hardly emulate any complex behavior of actual neuron. It is just implementation of a small subset of local learning function. And also there has to be the floating gate transistor itself is not very high speed. So now the flash memory technology, the floating gate transistor technology, at that point was very slow. Now we are getting much faster flash memory, right? So, and also at that time, the speed of signal or transmission for that single transistor they needed to achieve, it required a supply of 45 volt, which is unacceptable for any chip level implementation. Earlier version of floating gate transistor, before the flash memory came into existence, the operating voltage was in the range of 10 to 20 volt. That's why it was not acceptable. Initially, when we did microcontroller experiment, we had to take the microcontroller out of the motherboard, put it on a box of ultraviolet ray to erase this information using an ultraviolet light, because on the motherboard you could not apply 20 volt to reprogram it, it will burn the motherboard. So this one also needed a 45 volt supply to achieve the speed of transmission that can be. Further improvement of fabrication process for floating gate transistor reduced that operating voltage to 12 volt, but still it is not very desirable to have that high voltage, because then for a small nanoscale device it is significantly higher than its breakdown voltage, so it will destroy the device. So the problem here is we want to implement a synapse and a neuron. We are talking about requirements of billions of transistors, so we have to use nanoscale transistor. And for nanoscale transistor, we have to bring down this operating voltage less than 1 volt. So first of all, it is not able to mimic the complex behavior of the whole synapse. A small subset of behavior it can mimic, and then also its operating voltage, it's so bulky and it's very high voltage, its operating voltage need to be brought down below 1 volt so that we can use nanoscale transistor. But at such a smaller size with some such small voltage of operating voltage, can it mimic the actual synaptic behavior? That's the question. So, new ideas, people were exploring what type of synaptic circuit we need. We need synaptic circuits that has biomimetic behavior, not only like binary behavior, abrupt behavior, it can be able to follow the actual behavioral pattern of a biological cell. Small area and small size, so that we can implement high density neuron circuit. Because we are talking about billions, hundreds of billions of neurons, each neuron carrying tens to 100,000 synapses. So probably a complex cerebral cortex, even one neuron will need several billion transistors. Forget about complete cerebral cortex. So, and then the storage and computational capabilities must be integrated, because neurons, synapses, they are simultaneously a memory unit as well as a signal processing unit. So we have to meet these requirements, attributes to implement a real synaptic circuit. So one thing we concluded that digital circuits will not be suitable, because digital circuit is abrupt, noisy. So we need a continuously changing analog circuit to mimic the behavior of a neuron, a high density analog circuit. So people are working on many different types of analog floating gate differential pair MOSFET circuits to actually mimic behavior of silicon cortex or small units of synaptic cortex, that is synapse. So, one of the requirements for building an efficient synaptic circuit is, along with what we have discussed so far, it has to be simple. That means because you have to be able to connect all those individual synaptic circuit you are developing in rows and arrays to build a complex system so that you can build at least the biomimetic circuit for whole neuron and whole part of cerebral cortex. So that design must be simple so that it can be replicated again and again billions of times so that you can implement a large complex system. When you are talking about millions and billions of synaptic circuit arranged and connected in rows and arrays, they will be very, very densely packed and they will be severely affected by noise coming from all the neighboring circuit. So there has to be extremely high level of noise immunity inside your system, otherwise slightest variation, because human brain, you're talking about minuscule variations of signals going up and down continuously at a random order. So if a smallest amount of noise is injected, you lose your actual trace of signal. So it has to be very, very immune, noise immunity has to be very, very high in this type of synaptic circuit because it's a small analog circuit based signal and also it is continuously changing. So you have to make it very robust against noise. Another thing for any synaptic circuit design we have to worry about. Those who are working in biomedical area, you know that this STDP, spike time dependent plasticity rule. What does it mean? STDP rules, it is a set of learning rules observed in biological experiments. So people in the biological science, in biomedical area, they work with many different types of biological cells and tissues. When they apply different stimulus signal to those biological cells and tissues, in response they observe different types of reactions, behavior. And how to observe and how to quantify those behavior is guided by a set of rules in the biological world, and those are called spike time dependent plasticity rules. So the synaptic circuit that we are going to design must be compliant with those rules set by the biological biomedical researcher, experimentalist. Otherwise you cannot basically present your result in the framework that people will understand and people can validate, right? So, and these rules are not basically some random rules people set up. It's based on actual behavior, based on certain stimulus of biological cells. Based on that, like for example, in a simple current, if I apply a 10 volt voltage across 10 ohm resistance, I exactly know what range of current I expect, and to carry that current, to measure that current, what types of devices I need and what type of basically device can handle that 1 volt voltage. So these are determined by a set of rules that this device, it has a tolerance, how much electricity it can carry, how much voltage it can tolerate, right? So I'm just trying to make it as simple as possible. So these STDP rules, now there has to be a similar, like in the electrical world, in the biological world, there has to be some rules, compatibility rules, so that you cannot just randomly mimic any biological behavior using any circuit. It has to conform to this set of rules. So further elaboration of this STDP in biological process. So now, when a human brain cell receives any stimulus, it will adjust connections between neurons in response to that stimulus. And then how it will adjust, because these are elastic cells. Their electrochemical and electromechanical properties or strength will change. And as a result, those connections between neurons, those synapses, will adjust its strength of those connections based on the timing as well as strength of the stimulus that is coming out of those neurons. So that means which will determine its actions and reaction, inputs and outputs, and it will basically manifest it by creating a spikes, some potential voltage spikes, right? So the mechanical change of plasticity will be reflected by the production of some potential spikes, and those will be time dependent. So, and the rules that guides this time dependent plasticity behavior, they are known as STBDP rules. So, now the question is, so far, based on decades of research from biological scientists and biomedical experts, we know exactly what behavior to mimic. We know what factors to contribute. So we know all the design expectations, design requirements, right? So one of the biggest problems for any designer, any engineer is knowing what to design and knowing what are the attributes you have to achieve in that design, right? You are designing a microprocessor for 5 gigahertz speeds to do this function, graphical function or some other function, right? You know exactly design specification. So in this research area, we know everything, what to design and what attributes to take care of in that design, right? But then the problem is why we are not successful as of now. What technological challenges preventing us? If we know everything, what to design, what to mimic, what to implement, what factors to consider during the design, what attributes to achieve from that design, we know everything. But then why we are not able to implement the design as of today? So what is the technological challenge? The number one, the scale of human cerebral cortex is daunting, beyond the capability of any CAD tool, design tools or manufacturing process currently we have. Because we are talking about 100 billion neurons, each neuron carrying 10,000 to 100,000 distinct synapses, and then each neuron can fan out to almost 10,000 presynaptic terminals. That means it can potentially have 10,000 connections, 10,000 synapses, each neuron, right? So, now, currently, everything we implement, digital, analog or mixed signal, 80%, more than 80% are predominantly dependent on CMOS technology. So the CMOS technology, if you want to use the CMOS technology to implement these neurons, the size and the complexity and the density of that CMOS circuit that we will need, that is the beyond capability of any design tools or manufacturing process. So that's why CMOS technology is not possible. So we have to move out of silicon-based CMOS platform. So you have to look for a feasible non-silicon platform to actually implement a circuit of that complexity, even fraction of it. So earlier at the beginning of this century, people got excited and got optimistic because people started exploring many beyond CMOS and beyond silicon transistor and device technologies, and they're hoping that someday some of those technologies will become feasible and can be used to implement it. So, just to summarize what we need to implement this, we want to know how our brain behaves. Why we are doing all this? Because for disease identification, for threat detection, for many other purposes, we want to know how our human brain will react or will behave under normal and abnormal condition for many different reasons or factors. So that way, we will be able to develop many different drugs and treatments if we can apply different types of stimulus on an artificial brain, because it is not possible to experiment on a living brain. It is possible. By the end of the experiments, you will not see the result of that experiment, right? So, you can play with many other organs in human body, but you don't want to play with, because if you just destroy a small set of cell, that part of body will be permanently paralyzed or you'll be dead. So that's why people want to develop an artificial brain so that you can apply different stimulus and see the actions and reactions, so that you can basically address the abnormality, psychological problem, autism and other issues, and those permanent problem as well as temporary brain diseases by playing with this artificial brain. The problem with this, the brain sample that is collected from that person, that loses many of its properties right away. First of all, those electrochemical signals are no longer there. It's just a piece of meat. The problem is, many of these things we want to know about our human brain, many of these attributes, other than the anatomical and physiological some aspect, those dynamic electrochemical, electromechanical behavioral aspects, all will be lost as soon as we are dead. So the scopes of the experimental findings and understanding of complex human brain behavior under normal and abnormal condition is not possible by doing research on brain of a dead person. But it is not possible to experiment on a live human being or any live person. So that's why people are desperately looking for decades to come up with an artificial cortex to play with. Okay? So this is one of the research project. One of my former master's student, long time ago, he tried to explore, can we use carbon nanotube to design synaptic circuits? So the whole idea is carbon nanotubes are very, very strong. It has extremely high tensile strength. It's nanoscale. It consumes voltage at a fraction compared to a silicon device. So because of its nanoscale size, because of its very low voltage and very extremely high electrical conductivity, thermal stress, we think, and many other people, they thought that it is possible to develop synaptic circuit using carbon nanotube based device. So one of the popular thing among people who are researching in carbon nanotube is the carbon nanotube based field effect transistor. So some researchers, they tried to come up with synaptic circuit using carbon nanotube based field effect transistor. So Alice Parker, as I mentioned, one of the earlier biomimetic circuit designer, he proposed this synaptic circuit here. All of these transistors are not regular silicon transistor. Those are based on carbon nanotube based field effect transistor. So this group from UCLA and Stanford, two of the top research universities in the world. They tried to come up with this carbon nanotube based synaptic circuit. So if you are interested, you can look into their paper. I gave the reference earlier. So this, again, their problem is not the circuit itself, implementation of carbon nanotube based field effect transistor. If that implementation is feasible, then somebody can implement it and do the actual experiment on this. This is purely a simulation based design, not actual implementation. Okay? That's all. That ends the first part of our lecture on biomedical, and this will be multi-part lecture, and I will be posting all of these contents by Thursday. So I actually changed my plan a little bit in terms of our course presentation and paper submission. When is our spring break? Next Monday is next week is our spring break. So we will meet in this class again for continuation of lecture this Thursday. There will be no presentation, and then I will actually give you a much more detailed task in terms of paper submission and presentation for the week after spring break. So, but you will receive a detailed email from me. Expect this email by Friday. But
After the weekend or before the weekend?
This Friday, I will send you the instruction, and then it will be due 1 week after spring break. And we will meet Thursday again to continue this lecture. Okay? See you.